played any type of, external sports, not the video games which you guys end up, locked on, total wired in for hours and hours. That's not the type of game which you play off. The type of games which you actually play off are the outdoor games, where you actually, run, sweat, you get hurt yourself, right? And I guess you have come across this or heard about this, that my foot is broken or my hand is broken, right? So whenever there is an occasion corresponding to that, and why am I actually calling this occasion? Because in these kind of events, you end up witnessing one of the marvels of modern physics. That is your exposure to X-rays. Everyone has heard about X-rays, right? You use it for getting to know what's the amount of damage which you have done to the bone. So that's that. But it has other applications as well, scanners and stuff in airports and security checks. So roughly speaking, it has major uses throughout our daily life. What exactly it is and why is it of primary importance to us? Let's see that in this video. Now let's study X-rays. Now X-rays were discovered at the starting of the 20th century, and it caught the attention of everybody involved in the field of physics. The reason being, first of all, it had the wavelength. The X-rays have a very small wavelength, and second, it's tremendous application. We can use X-rays, or we actually use X-rays in many areas, in many fields. So because of artificial production of X-rays, we could use X-rays in any area. So that was the key point. That is, we had infrared, we had radio waves, and we had different types of electromagnetic radiation, each having different uses. But we got those radio waves or UV rays, infrared, microwave in the nature itself, and we came to know how to produce those things. But X-rays was solely produced where means the birth of X-ray. We witnessed X-rays when it was first artificially produced. We never witnessed it before. So that was the landmark, or that was the greatest achievement at that particular point of time. That is, an electromagnetic radiation was marked as invented rather than discovered. So that's the key part. So let's study more about X-rays. So as written, X-rays were discovered accidentally by Röntgen in 1895. Subsequently, he was awarded a Nobel Prize around 1901. Law, Henry, Lawrence Bragg, Vaclav Sigban. So these are the scientists which, or who actually gave a good amount of time and made tremendous contribution for the, production of X-rays and its application. That is, effective way of producing X-rays, and also how to use them in different fields. So as you know, X-rays are used in medical sciences for radiography to see if there's a fracture or there's any default in your bones, in your body structure. So X-rays are used for that particular purpose. So it's also used in ray spectroscopy and electron spectroscopy. Again, these are type of spectroscopy as in you shoot something at the atom or a molecule and you register its response. So ray spectroscopy involves a beam of light rays thrown at a particular sample and studying the response of the atom, how it scatters or radiates light. Electron spectroscopy, as the name suggests, it involves electron. So these sort of new ways of tweaking around with atoms and molecules were discovered as a consequence of X-rays discovery. So let's study more about X-ray. So this is the outlook of X-ray and what are its application and how was it discovered and everything. So let's study about how it was first produced. So experimental production of X-rays and Bragg spectrometer. So what happened is, in X-rays, you have electrons, and you don't have a normal electrons, you have fast-paced electrons. So the electrons are moving with a very high speed, tremendous speed. If I'm actually quoting tremendous speed, it is around 10 to the power 5 to 10 to the power 7 meter per second. That's how fast are these electrons actually moving. So these fast moving electrons, they are made to collide with a metal. So obviously metal of a particular choice, it can be tungsten, copper, nickel. So they collide with the metal and there is a radiation. I haven't told you about the reason behind the radiation yet, but please keep in mind that fast moving electrons made to fall on a target, a metal target, and subsequently the radiations are out, and those radiations which are out, those electromagnetic radiations which are out, they are called as X-rays. Its wavelength is an order of an angstrom, 10 to the power minus 10 meters. So, and the different material may lead into different types of wavelength, or different values of the wavelength of X-rays which we can get. So the type of X-rays which we get depends upon how fast the electrons are moving and what is the target on which the electrons are going to fall. Now this is how the setup actually looks like. So it's a copper bar. So this is my output, the useful X-rays, and the electron stream is over here. So the electrons from this end, they fall on this end and results into production of X-rays. So, and obviously the other arrangements are to make sure that the electrons, they do fall properly on the target, and the X-rays produced, they come out in in a fashion which we can use. And the other arrangements, anode, tungsten target, and everybody, copper bar, and these all arrangements are sort of coolant. I will tell you why do I need a coolant over here. So it's not mentioned in the diagram, but we do have a coolant attached to the setup. The reason being, I will explain you in the coming slides, so don't worry about that. So this is how the X-rays are produced. Now, what are the characteristics of X-rays? So X-rays, they have a wavelength around this much, 0.1 angstrom to 1 angstrom, and are produced when a metal anode is bombarded by very fast or very high energy electrons, and are not affected by electric and magnetic field. They cause photoelectric emission. That is, if we use these X-rays, we can have the photoelectric effect which we studied earlier. That is, these are the rays, or these are the radiation which are used for photoelectric effect. Now, what happens, and the reason behind you witnessing the production of X-rays, we'll discuss this right now. And all the questions which I said regarding X-rays will be discussed from this slide onwards. Now, the electrons are accelerated across a particular potential difference. So they end up gaining an energy EV. And HVM is, H is Planck's constant, VM is the maximum frequency of X-ray radiation. Okay, how am I equating this? It sounds ridiculous, right? How am I able to equate the energy of the electron to the maximum frequency of X-ray which I get, or the maximum photon energy which I could get of X-rays? So what I did right now, in a nutshell, I'm going to tell you. Electron is accelerated across a potential difference. So the total energy which electron has right now is EV before hitting on the target. VM corresponds to the maximum frequency which we get in the X-rays. We get X-rays. So X-rays, they have different frequencies. We end up getting different frequencies. The maximum one has the same energy as that of the energy of electron. How is this related? Or why have I actually written this? Remember, the only drawback of Rutherford experiment, or let's say, to put it in better words, what was the first drawback of Rutherford? Rutherford model said that electrons are moving in an orbit. But as I know, electron being a charge, performing a circular motion, is having a net acceleration. Net acceleration to a charge means charge will undergo radiation. Radiation results to the loss of energy, and hence it will spiral down to the nucleus. That was the drawback, or that was the first drawback of Rutherford model.
The bottom line is charge under acceleration loses energy, radiation, right? It loses energy. It throws out energy in the form of electromagnetic radiation. Now, what happens when fast-moving electrons hit on a target, a metal target? These fast-moving electrons that hit on a metal target, the electrons are stopped or deaccelerated, right? Their velocity, their speed changes, their velocity changes. Velocity changes means there is acceleration. If there is an acceleration of a charge, it means the charge will lose energy through radiation. That radiation which we get is X-ray. So X-ray is nothing but stopping of fast-moving electrons. So the greater the acceleration is, the more or heavier is the energy which I release. So if I am moving very fast and I am stopped suddenly or I am slowed down suddenly, then I will lose energy if I am a charge. So if I am moving very fast, so the energy which I will, very fast and I am slowed down, so I will radiating out good amount of energy. Photon will be of very high energy. Very high energy photon means that photon has very small wavelength, and that bracket or the range of values on which it falls around, that wavelength, the small wavelength, is that of the X-rays. So this is how X-rays are actually produced, and the reason why they are being produced is this: suddenly stopping. You're breaking it. You're stopping the electrons. Stopping electrons, acceleration, radiation. Intensity of X-ray depends upon the number of electrons hitting the target. Obviously, if more number of electrons are hitting the target, then more number of electrons are stopped. More number of electrons are stopped, more number of photons are released. More number of photons are released means intensity of X-ray. That's the intensity of X-ray. Now, cutoff wavelength or the minimum wavelength, where V is in the potential difference, is applied to the tube, is I minimum or lambda minimum is 12400 divided by V. Or let's say let me put this as wavelength lambda. So lambda minimum is 12400 divided by V. That much angstrom. Now, I've simply set off stuff, that is what is cutoff wavelength. I haven't explained you yet. So I will explain you right now what do you mean by cutoff wavelength and what the hell is this graph. First, this graph, in y-axis I have intensity, in x-axis I have wavelength. Now what happens is when electrons, the fast moving electrons, they are hitting on the target, I have a wide range of values of deacceleration, right? Let's say electron is moving with the speed of 1000 meters per second. Let's play ballpark. If it's moving with a speed of 1000 meters per second, it's slowed down to 0. There's an option. It's slowed down to 1. Again, another option. It can be slowed down to 2 meters per second. It can be slowed down to 999 meters per second. So I have a whole range of values available with me, right? And I know greater is an acceleration, greater will be the energy or energy released, or the energy of the radiation which is released. So it means the greatest, or let's say most energy, or let's say the highest energy which will be released, the maximum energy which will be released when the electron is stopped, simply stopped. It is at rest. It was moving very fast, now suddenly it is at rest. In this scenario, the amount of acceleration is too much, which results into too much amount of radiation loss, that is X-rays, or that photon or that group of photons will have the maximum energy when you are moving at the top speed and you have suddenly dropped dead to 0. In that case, the photon released has the maximum energy. Now, if that photon has the maximum energy, it means that photon itself is having the minimum wavelength, and that's what is depicted over here. For the minimum wavelength, that is, I cannot have a wavelength less than that. If lesser is the wavelength, this means greater is the energy. So this is lambda min, which corresponds to the maximum energy, Emax, the maximum energy. So you cannot have a wavelength less than that. Now, now this is quite rare, electron being suddenly stopped. This is a bit common, more common, and hence I will end up getting a value. That is, what I'm trying to say is, there will be an acceleration which is most common, right? Most number of electrons are undergoing that acceleration. Corresponding to that, the intensity of that acceleration will be the maximum. I will repeat. For an electron moving at a very high speed, dropping dead to zero is very less probable. That is, few number of electrons undergo that particular change. So there will be a change which will be most common, or most of the electrons are undergoing that change. Let's say that particular change is 1000 to 150. It means the photon which is released corresponding to this transition or this acceleration, that the number of photons corresponding to this dropping from 1000 to 150 will be the maximum. So intensity will be maximum for that particular breaking incident. Okay, that is, you are dropping dead. So if this is most probable, then intensity corresponding to this will be most. So this will result into a particular lambda. For that lambda, the intensity is maximum because it's most common, I have the maximum number of photons with this lambda. So hence intensity is maximum. Now what are these peaks? These peaks are called as characteristic peaks. What do you mean by characteristic peaks? These are characteristic to the target which we are using. If you bring in a different target, you will end up getting a different characteristic peaks. These peaks are basically because of the transition of electrons at inner levels, inner shells. So K alpha, K beta corresponds to that transition of electrons moving from one orbit to another orbit. See, so X-rays, the spectrum which I will get comprises of two things. One, irrespective of target, I am simply slowing down because I collided with somebody. I don't know what that object is. I collided, I slowed down. Correspondingly, there will be radiation loss depending upon how much I have slowed down, which is this continuous spectrum. And the second is, few electrons, they actually nudge off an electron. So it's like if I have a fast moving electron, I go inside an atom and I nudge out an electron. So when I nudged it out, then there will be transition. The higher shell electron will try to come in with the lower shell, right, resulting into the radiation. So a photon is released. So if that photon is characteristic to, or it's unique to that particular target, hence the total spectrum which we get is because of electrons slowing down plus because of electrons inside the target making a transition. So it's a summation of these two. So as I said, this is continuous spectrum. Irrespective of what target you use, you will end up getting this. Then continuous spectrum. Then comes characteristic spectrum. Depends solely upon the nature of the target, what the target is. So do keep in mind what are these graphs and what exactly X-rays are. Moving on. Continuous spectrum due to the retardation of, as I said, continuous spectrum is due to the retardation of electrons. Characteristic spectrum due to the transition of electrons from higher to lower level. Bragg's law said that 2d sine theta is equal to n lambda. Why I am bringing out Bragg's law is because of the fact the same 2d sine theta is equal to n lambda is this kind of a similar expression which we witnessed or which we observed while dealing with Davison-Germer experiment. Now, remember what we did in Davison-Germer experiment, electrons thrown on nickel crystal. Here, I have the same thing going around. Electrons, fast-moving electrons thrown at a metal target. So, I might expect some scattering in at a particular angle. So that's why I'm bringing in Bragg's law to find out at what angle it will be favored. So at that angle, I will keep my outlet such that the X-rays are taken out. That's the reason I'm bringing in Bragg's law. So please make sure that the production of X-rays is quite similar to the Davison-Germer experiment. Is actually the Davison-Germer, the pair derived their inspiration of the setup for testing de Broglie idea from X-ray production. So they use the Coolidge tube, the tube used for production of X-rays, for carrying out the experiment for proving de Broglie's idea. So as I said, my intention of bringing in finding out theta is to find out at what angle will I get the maximum intensity. So at that particular point, I will keep the outlet or keep the detector to know that. Now, binding energy, as I know, binding energy is equals to minus of total mechanical energy. So these are the few attributes or few facts you should know while working out a problem on X-rays. Binding energy is equal to half minus of the total energy. Velocity of electron is this. V is equal to c by 137 n. N is the number of nth orbit, number of the orbit. And for X-rays, lambda is this. Series limit of series means minimum wavelength of that series. Yeah. So series limit, obviously, as the name suggests, I have my Lyman, Balmer, Pascher is the same series which we are talking about over here. So don't by heart these facts, just know that they do exist. Right? These are not that important, but just make sure that you know what these facts are. Now, production of continuous spectrum, as explained earlier, according to Maxwell's theory, if the charged particle is accelerated or deaccelerated, they emit radiation. Now, and this is called as Bremsstrahlung. It's a German word meaning breaking, right? Radiation due to breaking. Actually, the complete translation of Bremsstrahlung is light because I stopped. There is light because I stopped. So that's the meaning of these type of radiation. Bremsstrahlung radiation. Bremsstrahlung means light because I stopped. So that's purely similar to what we are doing over here. Electrons are stopping and this radiation as in light. Now, moving on, when the whole of the energy of electron is converted to the radiation, one gets the maximum energy. As I said, 1000 to 0, I get the maximum energy I want. If V is a potential difference applied, it is converted to the kinetic energy of the electron. So EV is the energy, E is equal to H nu is the energy of the X-rays which we are getting. So this is the wavelength which we will get. So it's simple, as I told you. It all depends upon how much energy of the electron is, how much energy the electron has actually lost. That will be thrown out in terms of radiation. Now, again, simply put out the values of HC, everything, you will end up getting lambda min to be this. It's very simple. As stated earlier, we did this, that is EV, energy of electron, when it's about to make contact with the target. That is being totally robbed off. It stopped. That is converted into radiation. Radiation has an energy, Hc by lambda. And this is the minimum, because EV is the maximum energy which I can lose. Right? I cannot lose energy more than that. So, from this particular expression, we end up getting this. Okay. Now, the reason I told you in the setup, in the Coolidge tube, there should be a coolant or a sort of system which makes sure it is maintained at a particular temperature, because it's very few electrons which are actually undergoing this Bremsstrahlung or the breaking radiation. What they usually undergo is they hit the target and simply results into the rise of temperature. They heat up the target. So it's so the fast moving electrons carrying so much energy, striking at a very quick rate, the intensity is also high, so that will simply melt the system if I don't have any proper coolant or cooling system associated with it. So that's why a proper cooling system is there when we are carrying out an expression or let's say an experiment on X-rays. So now the maximum value of the intensity is approximately 3/2 of the minimum wavelength. Right? Now please note it over here that it is 3/2 of the minimum wavelength. the maximum value of intensity. Now that's the same point which I was talking about, and is transition from 1000 meter per second speed of the electron to 0, it's quite rare. So there is a particular speed, so the maximum value of the intensity will correspond to the maximum number of photons released. So if lambda naught is the wavelength for which I have maximum number of photons, it means I have the maximum value of intensity. Now that lambda naught is actually 1.5 times of the minimum wavelength. So this is the wavelength for which I get the maximum number of photons, or this energy, the photon carrying an energy whose wavelength is 3 by 2 lambda minimum, is corresponding to a transition from a very high speed to a particular speed. That is the most probable breaking incident, from 1000 to, let's say, 40, 60 or 200, 1000 to 200. If that is the most probable breaking phenomena, then corresponding to that a photon released, so the number of photons released corresponding to that particular breaking incident, the intensity will be maximum. So in case of X-rays, I have 1.5 times the minimum wavelength. This is often marked as lambda minimum. Actually, it is not the minimum value of wavelength, but the intensity is maximum. But the intensity is actually maximum. So make sure that you understand few of the terms over here. Intensity. What's the meaning of intensity? First, you should understand the cause behind the creation of X-rays. If you have properly understood the reason why X-rays are generated and why different sort of wavelengths, I end up getting different wavelength, then you can clearly understand the maximum intensity, minimum wavelength, and other stuff associated with it. Now, the distribution of intensity depends upon the material of the target, the current, and the potential difference. So these I is or intensity is proportional to V square, and intensity is also proportional to the current. Now, let's try out a question based on this particular phenomena. So I have an X-ray tube which is operated at 40 kilovolt, and the heat is generated at the rate of 720 watt. Assuming only 0.5% of the energy of incident electrons is converted into X-rays. So I know that the heat produced is 720 watt. Right? This is the rate at which the heat is produced, dQ by dt. Right? This is 99.5% of the energy. 720 watt is the heat produced. It means that the 99.5% stands for this. That is, whatever energy I am sending, 99.5% is getting converted into heat. Only 0.5% is utilized. So I know that each electron is having an energy EV. This is the energy with which it actually hits the surface. Now let's say this energy is totally converted into X-rays. Then EV results into X-ray production. Now I want to know, let's say there are n number of electrons which are undergoing deacceleration or breaking, which results into production of photons, a group of photons. Now that particular energy is equal to 0.5% of the total energy. This is 0.5% of the total energy. I know 720 watt is 99.5% of the total energy. If 99.5% of total energy is 720 watt, then how much is 0.5% of total energy? Right. So again, with the help of unitary method, we can find this particular fact. Let's say we call this as Y. So NEV is equal to Y. Let's say I call this as Y. So I can easily get the number of electrons which are effectively undergoing that transition. So Y equals to EV. Now I want to find out the number of electrons per second striking the target. These are the number of electrons which are actually hitting the target and also undergoing the acceleration, which results into production of X-rays. So N stands for the number of electrons contributing for X-ray production. So how can we find out the number of electrons actually hitting the target? That will be more than that. I know that the phenomenon of hitting electrons results into two activity, one being production of X-rays, the other being the production of heat. Now I know that the production of heat and X-rays are directly related to the number of electrons, and number of electrons contributing towards X-ray production and number of electrons contributing towards the production of heat. If more the number of electrons are producing heat, it means less number of electrons will be producing the X-rays. So I can clearly say that the ratio of this 0.5% of energy towards X-ray production and 99.5% towards the production of heat, that's the same ratio which I have with the number of electrons responsible for production of heat and number of electrons responsible for the production of X-rays. So this particular factor, so N over here, which we got, let's say I write as Nx, the number of electrons contributing towards X-rays, is basically 0.5 divided by 100 into the total number of electrons. Now if I work this out, I substitute this over here, I can get the values of the number of electrons. Not doing the calculation, so please make sure that you end up doing the calculation. So, and the velocity of the incident electrons. Now what is the velocity of incident electrons? I know that they are being accelerated by this particular potential, that is equals to half mv square. I know the mass of electron, charge of electron, the potential across which they have accelerated. I know the value of 2 as well, so I can easily find out what is the velocity. So the velocity will come out to be 2 ev by m.
Now let's note down the things which you have learned about X-rays in this particular video. First thing first, the genesis of X-rays. How does we produce X-rays, and what are the different types of wavelength which we get while production of X-rays? We kind of found out that characteristic and continuous spectrum. What are these things? What are the factors which governs these characteristic and continuous spectrum? And also we studied about the uses as well. So now we're done with the complete package of X-rays. Now the only thing left out for me standing over here is observing the atom. Okay, fine, I am observing the atom. Am I done with everything corresponding to atom? Let me see. I know its structure. I know what it's made of. I know what will happen if I throw the light. That is the only way I can disturb the atom. So I know everything about atom. Now the basic question is, what is inside the atom? I know electrons are moving around the atom, but what exactly is inside the atom? Inside the atom, you might say, okay, inside the atom, I know through the Rutherford's model and also through Bohr's model, it's nucleus, collection of protons and neutrons. So it's nothing special about it. It's guarded by electrons. I don't think so. There are some events which are directly correlated to one present in the center, the nucleus. So let's find out about what's going inside the atom at the innermost core of the atom.